viewers, myself Dr. Preeti Jagwani. I am Assistant Professor from Department of Computer Science, Aryabhat College, University of Delhi. I welcome you all for CEC lectures. So today's topic is a greedy technique, and particularly we are going to see about Kruskal's algorithm. So in previous lectures of us, we have started exploring the greedy technique or greedy algorithms. So in this greedy algorithms, we have seen in our previous lectures that this is basically an kind of say short-sighted non-recoverable algorithm which generates the solutions in a piece by piece manner, and at every step of generating the solutions it is looking for the maximum benefits. That's why it is known as a greedy algorithm. Now, among the applications of greedy algorithms, we have also seen the concept or the fundamental principles of spanning trees and minimum spanning trees. While coming to the spanning trees, if we are looking for spanning trees, we can say we can go through best first search, breadth first search and depth first search. But as far as minimum spanning tree is concerned, minimum spanning tree, in order to determine the minimum spanning tree, we have some different algorithms, and in the list of that those different algorithms, two are very famous, we can say, or prominently used. So those two algorithms are Kruskal's algorithm and Prim's algorithm. So today's agenda is Kruskal algorithm. So Kruskal algorithm, as I have told you, that this is basically an algorithm to generate or to determine or to find the minimum cost spanning tree or minimum spanning tree of a given graph. So basically this what this Kruskal algorithm does. This Kruskal algorithm consider the graph as a forest and every node as an individual tree, and every tree, which is basically a node here, is connected to, will be connected to the another only and only if it is having the least cost among available options. So basically our Kruskal algorithm is picky about looking for the least cost edge among the all available options, and for this the whole graph is considered as a forest and every node it is considering as individual trees, and one tree will be picked, or maybe we can say two trees will be picked if the connection between those trees is the edge having the least cost among all available options. But along with these constraints, or along with this, I can say operating procedure, it also must not violate minimum spanning tree properties. So must not violate minimum spanning tree properties means it should not generate, or it should not end up in a cycle, because then it will no more be a tree. As we are talking about minimum spanning tree, it has to be a data structure which is kind of acyclic. Now coming to the operating procedure or operandi of Kruskal's algorithm. Basically, as it is a greedy algorithm and we are picky, or we are being choosy in taking up the edges, we are looking for the edge which can give us the maximum benefit. Maximum benefit in terms of maximum benefit for minimum spanning tree will be the edge having least weight. So in order to determine the edge with the least weight, which we need to consider within our minimum spanning tree, first of all we will sort all the edges in an increasing order according to their weight, so that we can see that whether we are going with one option or we are going with two option number 2 or option number 3. So what is the why should we look for why should we ignore some of the options, because they may violate the minimum spanning tree properties. I will just explain this with the help of a figure. Then among all these sorted edges, the smallest edge will be picked up and it is checked for the cycle formation, and if a cycle is being formed, as I have told, that particular edge will be ignored or will not be considered. Edge will be included if and only if the cycle is not formed, else we can discard it. And this we will be doing, that means we will picking up the smallest edge, including it in the minimum spanning tree while checking for the cycle. That means we need to repeat this step number 2 until there are v minus 1 edges in the spanning tree, because we as a spanning tree, if I give you a one liner recap, it is a tree with all the vertices which are present in the graph spanning over all the vertices, but the number of edges will be v minus 1. So, we will keep on repeating the step number 2, which is picking the smallest edge and checking for cycle formation. If it is not forming the cycle, include it as discarded. This process will be repeated until there are v minus 1 edges in the spanning tree. Now, why are we saying Kruskal's algorithm as a greedy algorithm, or how I can say this Kruskal algorithm is going to qualify as the greedy technique or a greedy algorithm? Because in each step we are adding the next lowest weight edge that will not form a cycle to that particular minimum spanning forest or tree. We can say forest also, because the intermediate results we can say can be disconnected also, but the final result we will be having a tree. Now because final result we will be having a tree, because ultimately we will end up with v minus 1 edges in that spanning tree. So, v minus 1 edges in a tree, that means it will be connected, but yes, at the intermediate steps it could be, you can say it could be a forest. At the termination of the algorithm, the resultant forest has a single component, as I have already told you, and forms a minimum spanning tree if the graph is connected. So, here as our first example, we are assuming that the graph is connected. So, graph is connected, that means we will be having minimum spanning tree, which is a single component in the resultant forest. Now, coming to the example, here I am having a graph which is connected with some vertices A, B, C, D, E, F and G. So, basically 7 vertices, and as the number 1 step says that we need to sort the edges according to their weights. So, if we can see in the table which is lying below the graph, we have edges and the corresponding weights, which is 5 for AD, 5 for CE, then we have 6 for DF sorry, then we have 7 for AB as well as for BE also, and so on and so forth. So, basically this is the step 1, or this is the list of the edges in their increasing or non decreasing order of their weight. So, what are we going to do? We are going to pick the smallest edge. So, if we pick the smallest edge here is, let us say, AD. So, we have picked AD, and then after picking AD, again we will be picking the next least edge, which is CE. So, we will be picking CE also. So, now please imagine in the graph we have AD as well as CE, no other component is included in the graph presently. So, we have AD as 5 and CE as 5. Now, apart from that, we will look for the next step or the next edge which is the least among the all possible available options. Now we have already covered AD and we have covered CE also. So after that we will be covering the edge which is DF in the list, and DF is having the weight 6. So now we have AD, DF and CE. Now coming to our next step, which is taking AB. So AB is again having weight 7, which is the least possible among all available options. So we can take AB as 7, and yes, please remember that at every step we are also checking for the cycle formation. Considering the first step AD, no cycle is there, because in any case we have just started with, there is only one edge available in the minimum spanning tree, which is AD. So no cycle there. Then we have CE on the right hand side, so we have 5 for that. These are also not connected. Cycle formation is no question here. So CE we have taken. Then we have taken DF. So DF is although having a common vertex with AD, but still it is not resulting in any kind of cycle formation. So DF is also okay. So DF we have included in our minimum spanning tree. Then we have AB. So AB is having its weight as 7, and it is also sharing a common vertex with AD, but still it is not kind of we can say it is not covering, it is not resulting in any cycle formation. Now coming to BC. BC is having its weight as 8, and it is sharing a common vertex with the edge CE. So yes, BC we can safely include because still with the edges DF, AD, AB and CE, including BC is not going to result into any of the cycles. But now let us consider the next step, which is FE. FE is the next edge in the list of sorted edge weights. So please understand what is going to happen the moment we introduce FE into our minimum spanning tree. What is happening is you can say now it results in a cycle formation, which is a cycle in terms of from A to B, then C, then from C to E, E to F, F to D, and then D to A again. So the moment we introduce EF edge here, it will result in a cycle. So definitely we are not going to consider this, because we are looking for a minimum spanning tree. It has to be a cyclic, and in order to make it a cyclic we have to avoid a cycle. So FE basically we are not going to include. Now coming to the next edge, which is EG. Now if you can say EG, yes, we can safely include, because EG will not result into formation of any cycle. But again, the next thing, which is for DB. So the moment we introduce DB, we form a cycle A, B, D, A. So because introduction of DB into our minimum spanning tree is resulting in a cycle, we need to ignore the edge DB. Now coming to our next edge FG, and yes, where are we going to stop this? We need to check the total number of edges. So when our total number of edges are going to be equals to V minus 1, that is a kind of a programming indication, we can say that yes, all the vertices have been covered. So with every step we need to check two things. One is whether the number of edges included in minimum spanning tree has become equals to V minus 1. If not, then we will continue, and if it has becomes to V minus 1, that means our minimum spanning tree has covered all the vertices, has spanned all the vertices. Another point which we need to take care of is, or I have already told you, that is cycle formation. So in case of FG, we will see again a cycle will be formed, that means we are not going to include, and so as DE. But before this FG and DE, I can say my requirement of V minus 1 edges, because here we are having 7 vertices. So 7 vertices, that means we are happy with the 6 edges. So 6 edges we have already included. We have AD, we have AB, we have BC, and then CE we also have, and then EGS, and then DF. So basically we can say all the vertices have been covered. So as all the vertices have been covered, we can always stop our algorithm here. Now how to stop the algorithm and how to go about all these implementation, I will be covering in next 2-3 minutes. So if we can see here, we can see some dark edges and some some thick edges and some thin edges. So we can identify that these edges are not to be included. For example, DE we need not to include, then we need not to include DB also, because all these will result in a cycle formation. So basically these vertices, so coming up to the minimum spanning tree, it will be having the edges AD, BA or AB, we can say, as it is an undirected graph. We can have BC only if it is not resulting into any cycle formation. Then we have BE, then we have CE, DF is already there, and then we have EG. So basically 6 number of edges, and we are done with our minimum spanning tree. So in this way the Kruskal algorithm operates. So although we can take another examples if the time permits, but before that let me come to the pseudocode in Kruskal's algorithm. As I have already told you that intermediate result could be a forest, so that forest F is taken as phi. So looking at the pseudocode, we can say initially we have taken a data structure which is basically F representing a forest here, and that is null here, and for each vertex belonging to the vertex set of the graph, we need to do a step of make set V. Now what this make set V is doing, I have told you that each and every vertex within the Kruskal's algorithm is considered as an individual tree, and the whole graph is considered as a forest. So make set V here means we are considering every vertex as the individual tree, and the whole graph as forest. So for every vertex we have made a separate tree, we have made a separate set, we can say. And for each UV, that means for each edge in the edge set, which is G dot E, and that edge set, as I have already told you, is ordered by weight in the increasing order. So for within that list containing edges in the increasing order, for that every edge we need to check if find set U not equals to find set V. Now what does it mean by find set U not equals to find set V? So basically this step is here in order to check that we should not end up in having cycles. So if this set of U and if the set of V, where this UV is the edge which we are considering, are same, that means these are belonging, introducing the edge UV will definitely result in a cycle. Then if the find set U is not equals to find set V, then only we will include this UV edge into our forest or into our result, which is, we can say, F will becomes F union UV. So we are going to consider, we are going to take it up this UV edge if and only if we get find set U not equals to find set V, which is a step to check whether they belongs to the same set, and if they already belongs to the same set, then again introducing one edge is going to result in the cycle. So we will avoid we need to avoid that. So if and only if find set U not equals to find set V, then we will include that edge by saying F is equals to F union U comma V. Then ultimately we need to take union of find set U and find set V. So summing up what we have done in this particular algorithm or in this particular pseudo code, we have first sort the edges by weight, as we have seen in the example also, using any comparison based sorting algorithm, and that is going to give us n log n time. So n here is basically number of edges, so we can say it is order e log e time, and after sorting we need to remove the edge with minimum weight, and that picking the minimum weight edge can be operated in constant time. So if we want to analyze the running time complexity of Kruskal's algorithm, we can say sorting is going to give us e log e, or in terms of n log n, it is going to give us order of e log e time, and after sorting, picking the minimum edge is obviously a constant time operation. Now looking at that make set V and find set V operation, as well as the operation of union, all these three operations, make set, find set and union operations, are known as disjoint set data structures operations. So here disjoint set data structures are also used as far as implementation point of view is concerned. So disjoint set data structures is used to keep track of which vertices are in which component, that is find set V and find set U. The step here is being referred to. Then we need to place each vertex into its own disjoint set by make set V, which is going to take order V operations. So total time, if we sum up for all these operations, is e log e time, or we can say equivalently e log V time, where E is the number of edges in the graph and V is the number of vertices. So complexity of we can say Kruskal's algorithm is actually e log E or e log V, which is taking consideration into consideration the make set operation order V. The make set operation for every vertex is an order V operation. Then disjoint set data structure used to keep track of which vertices are in which among which under which components. So that disjoint set data structure operation, find set U and find set V. So summing up all those complexities, we end up with having e log E or e log V time. And considering a graph which is, we can say dense, we can say E is at most V square, and taking log, we can say it is 2 log V. So finally E is of order log V, because we avoid the constants, or we can say we ignore the constants when we talk about a function in order terms. Then each isolated vertex is a separate component of minimum spanning tree here, and isolated vertex, how many vertex we are going to obtain, is obviously equals to V, because for every vertex we are making it as an isolated tree or isolated vertex. So V is anyways less than 2E. So log V is we can say log E. So in implementation, considering the implementation point of view of your Kruskal's algorithm, we need to be careful about a couple of things. First is we need disjoint set data structure to achieve the desired time bounds, otherwise we will not end up with having order E log V times. And after sorting, we need to put each vertex into its tree, which is very clear, and this can be done via calls to make set function, which is of order V time. Then we need to iterate through all the edges in the sorted order, and for each edge we need to determine that whether the ends belongs to the different tree or already the tree which has been covered in the previous steps. So this will require two find set calls of order 1 each. Then we need to have union of two trees or two sets for this data structure, disjoint set data structures functions, and this will be order 1 obviously. So ultimately we end up with having order E log V for sorting plus V for V calls for your make sets, and then E calls for your the other disjoint set operations. So finally we have E log V as the order E log V is the time complexity of your Kruskal's algorithm. In the worst case, even if we iterate through all the edges, we find we have two find operations and possibly one union. So even a simple disjoint set data structure such as disjoint set forest with union by rank can perform order E operations in order E log V time. So total time complexity is order E log E, or we can say it is order E log V. Both will do for in case of Kruskal's algorithm. So here in this lecture, let me sum up the whole thing. We have seen a very brief recap of greedy techniques and minimum spanning trees, and within this minimum spanning trees we have picked one strategy, which is Kruskal's algorithm. We have seen it with the help of an example. Then we have seen the whole pseudocode and analyzed the time complexity of that Kruskal's algorithm. Thank you for the patient hearing. Hope you have enjoyed the lecture. Thanks.